me prepare your stuff. So it's not in DSU, it's one of the grants opportunities, and for some of us it's just a pleasure and honor, and for some of us it is survival question. So there is a season of applying to proposals, and there are specific hints of what is expected, what is needed there. So some of the things that are requested by the different agencies, they might migrate from one agency from another, and the goal of these hints is manifold. From point of view of agency or community, maybe the humankind needs new knowledge and fluff stuff like that. But from selfish point of view, I see it as a little pushing mechanism that brings me out of the comfort zone, and to look once again if we have in our methodology, if we have perfect tools, so we can improve them. And because applying to grants is necessary, and can be just blindly apply methods that we are already doing. Are they competitive, or they're missing something? So, so the deadline is literally in a month from now. And some of them, there is a list of open calls, and there are two things that are very new, very challenging, and induce the interest and necessity to improve and develop something. So one keyword is topological insulators, and I can share the slides, and it's all public materials, nothing is from secret sources. So I have copy-pasted a couple of Google slides that I will show in maybe 15 minutes, and later we will discuss how, if the methodology that we are practicing can be applied to this code. They tell us some hints that can look through and adjust. But before these new keywords, new materials are really throwing off. Like I saw them before and tried to leave them behind, not to look at them because they're scary, because they're new. And looking on the calls, I also was trying to avoid it, but since situation proves that some submissions are needed, so there are like whale semi-metals, terminology from different community. So this all comes to the umbrella of quantum materials, which there are no strict definitions, but it is the understanding is that by mixing together objects or interactions of known nature, one can observe some new unknown phenomena. It's concept of emergence. And among these quantum materials, primarily they mention topological insulators and graphene. So if we open the Wikipedia page on the graphene, or it will prompt to Dirac cone, and there is a suggestion, there is a prompt from this open public information, and even doesn't need to go deep into professional literature, that things that we are doing are cool for certain range of applicability, for molecules, for quantum dots, but if we want to jump into activity of these materials, there are things that are missed, that are not included or on the way to be included into the methodology that we all are practicing. So for this type of materials, it is critically important to include the moment of dispersion, the dependence of orbitals on momentum, and they are more rich than one-dimensional, more rich than nanowares. They're at least two-dimensional. So the main key feature, I was trying to do ugly hand drawing last time, but here is something from public. So like this lower surface is HOMO, upper surface is LUMO, and the minima of the LUMO and maxima of HOMO do have discontinuity in the derivative. And later on, if we look through the text, it tells like in the vicinity of this Dirac cones, the carriers have zero mass. Zero mass, which it means that one can apply zero energy to accelerate them, so they will move freely. And it comes close to the concept of superconductor, when one doesn't apply energy to keep currents. And just in case, the kinetic energy is assumed as square of the momentum in regular free space, right? Then the second derivative of the kinetic energy will be curvature of this parabola, and it will be one over mass, right? So if it is a parabola, then it will be, the second derivative always will be some finite number. But since here the shapes, they are not parabolic, they are cones, and in the point where they intersect, the second derivative will be infinite. So if the 1 over mass is infinity, then mass is 0. So if one learns how to utilize this feature of electronic structure, one can avoid losses. And it looks like one of the goals, to have the frictionless electronic transfer. So for the two-dimensional materials with Dirac cones are more simple to understand and more popular, but there are analogous features in the momentum dispersion for three-dimensional materials. I'm just telling what I was reading. It's not my area of expertise, but there is need to look there. And in case the features of the dispersion similar to Dirac cones are observed in three-dimensional things. And what are those features? The energy is not quadratic but linear in momentum, right? So for the cone, there is a constant slope of this dependence of energy on momentum. Same as for photons. Like for electrons, typically it's parabola, and for photons, massless particles, the dispersion is linear. So if there are three-dimensional linear relations between momentum and energy, it sounds from this article that it's called while material and wild points. And also, I'm trying to look around what are the popular materials instead of graphene, molybdenum, sulfur, disulfide. So what are materials that show these features? Close your eyes and do not look. So Aaron is and Yevon are practicing spinners, and those are two-component spinners. But there is if one deals with, we are doing with electrons holes, and they all have energy about the same as visible photon. If one would look for energies like a couple million times bigger, like mega electron volts, then equations are somewhat similar, but instead of electron and hole, there will be electron and positron. They are coupled, and one uses combined object as analogous to spinner, but instead of two components, there are four. And those are it's Dirac equation for this four spinners, and there is some connection that I didn't study, so I just blindly copied. This looks very similar to Dirac equation, but probably if one looks carefully, it will be something different. So it's one spinner and two spinners composing are entering into the four component object. And if one processes it further, one can find that dispersion will be not quadratic, the energy frequency not quadratic in momentum, but linear. So if this feature is seen for electrons, it's considered cool for today, fashionable. And there are some ideas how to use them. So I'll skip through a couple of the slides because it's very far. I look forward to study them. There is everyone tells about the concept of arc. So there is a way for charge carriers to migrate from one of this special point to another, and there are experimental evidences of these arcs. With a scientist from Bangladesh experimented from. So, if you have connections to this country, maybe it's your destiny to work on oils and metals. And there is a discussion of how conductivity can change abruptly in the materials with this cone-like dispersion relations. Okay, I'm done. David, do not take example from me. For second year seminar, one should do much more thorough and higher quality review of literature. I wouldn't deserve any good grade. So invest time. So what can we do at our side to maybe approach this area? So on one hand, if it is one point and there is just without any expertise in this area, one point in the dispersion space, there is no chance that charge carriers will stay at a point. There are dynamical processes that accelerate, decelerate. So typical thing is to look if there will be some motion in the vicinity of this point, if in the phase space, on one hand. On another hand, if the there is no resistance. If currents can persist for a long time, most typically are not linear currents but circular, that are created by changing magnetic fields, as done in levitation experiments for superconductors. So if we want to adjust our suite of codes for electron dynamics toward these effects, we do need two key features. One that is being developed by Fatima for explicit inclusion of momentum, direct and indirect transitions. And second, explicit inclusion of magnetic field, which is a source of circular motion. In this aspect, there is a niche in the community. So because of objective difficulties, so magnetic field is not challenging itself. It's part of the 300 level courses for electrostatics. But if one wants to combine magnetic field with electronic structure calculations, it is objective challenge not in theory but in how to implement it. So magnetic fields coexist with currents, with charge density moving. I know that we are describing motion of charge densities, but typically we are looking for like transition from donor to acceptor rather than continuous currents. And in presence of magnetic field, the changing magnetic field, there are persistent currents, charge densities, and they affect electronic structure. So one does, in order to naturally include magnetic fields, one needs replace, like even if you do not go beyond above DFT, so density functional theory. Instead of density, one needs to use current density, C DFT. And then current can go in any of three directions, so there are more components. And for electric magnetic fields also there are components, so it's just more heavier object than regular DFT. And one day there will be software written by someone for public use, but it's not available today. So, and making universal software, it's too hard for a small group. It needs like big institution. But we can make a shortcut and combine outcome of regular DFT with some home-grown simple scripts that will mimic effect of magnetic field. So if we are looking on planar materials, then magnetic field is bundles with angular momentum, right? That composed of mixing of position of momentum along different directions. And the same thing can be done for in momentum space. Why we need momentum space? What is the reason? What is the benefit? If we go into coordinate space, things are a little easier and more intuitive there. But then if we want to import the specifics of material, then one needs potential. And potential is defined in too many points. And it is potential for one electron, while we are describing many electron problems. So it will be, it's pity that London is not here, but you saw from his works that he did before starting DFT that just David did this too, right? Importing lock-pot potential from VASP and trying to find eigenstates in that. They are maybe qualitative, somewhat similar to reality, but they will be never close in quantitative values. So it is extremely rough approximation. But if we are going to consider everything in momentum space, one can import, one can use already diagonalized information about dispersion. So energy as not as a function of position, not potential energy, but energy as a function of k points. And they are higher order information that includes all interactions. In software that we use in VASP, the k points are integrated part, and we can just use the momentum dispersion as grid points and in this space of momentum to explore dynamics in a similar way as Fatima was doing for one-dimensional nanowires. But here it will be more points because it will be 2 dimensions. Like if there were 4 in one, 4 in another, it's 16. And to have the circular motion, maybe instead of 4 by 4, it should be like 50 by 50, something like that. Which is a little scary for big materials, but if it is graphene, if it is smaller unit cell, it should be possible. So, did anyone try to run this code that was shared? It's fine. So, we all are practicing for a long time one-dimensional wave packet dynamics, and it's not a big problem to add second dimension. If there is no coupling between motion in 2 dimensions, it's almost evident. The only thing is to add, if we need circular motion, then one needs to couple motion in x and y. So this slide shows preliminary results of 2-dimensional dynamics in 2-dimensional free space. Why? 2-dimensional free space. We may want to combine many things which is too ambitious. 2-dimensional things, circular currents due to magnetic field, and the features, electronic structure features specific for each material, and later on the dissipative processes due to interaction with phonons. Everything at once is a little scary. It's better to divide and conquer and debug little things first. So here are two dimensions. Initial wave packet in each of these panels is the same, and those are isocontours. Same as we plot orbitals with isosurfaces, like 3-dimensional object is represented by surface. Isocontour is when 2-dimensional object is represented by line, right? So it's a value when wave packet has certain height. We should interpret it as a little Gaussian in both x and y. I'm not a good painter, but it's a little hump here. And the panels differ, they are the same with the initial condition. This initial wave packet has non-zero momentum in both x and y. And the difference between panels is different values of this model magnetic field that is implemented with angular momentum and dipole interaction. So if the magnetic field is small, then the wave packet does two things, 2-dimensional wave packet. It moves linearly forward according to by inertia, according to initial momentum, and it slightly expands due to Werner-Heisenberg uncertainty. In free space, the width of electron increases. If one adds a magnetic field of different value, then by this Lorentz force, it starts curling. And the larger the value of magnetic field, the shorter is radius of curvature. So it makes more and more sharp turn. It's like driving straight and then turning. And also it speeds up, the motion becomes quicker, so magnetic field accelerates. It does, the energy is conserved. But if you have the same kinetic energy and you move on the lower orbit, like if a ballistic missile, well, something peaceful. If a satellite needs to be deployed and burned in the atmosphere, when it comes closer, it goes quicker and quicker. And those are snapshots. Those ISO contours are made at each step, and there are trajectories. So if magnetic field is high enough, it's like 0.3 in some atomic or arbitrary units, it makes a full circle. So it's persistent current, energy is conserved, but it moves constantly. So this is the same thing. So it's motion of the wave packet in x and y, and in presence of magnetic field, it makes curved motion. So here is a slightly different initial conditions, initial momentum and value of magnetic field. Therefore, the combination of linear motion, expansion, and this curving due to magnetic field contributes, and it loses its nice shape very close, but soon enough it will be represented as set of circular orbits of different radius, which are solution eigenstates for this Hamiltonian, and those are Landau states. Oh, I should include this in the video page as well. So it goes around. If one reproduces the same simulation in momentum space, if you are doing it in a free space, there is no way, no need to draw potential, because in free space potential is zero, and magnetic field is not conservative. You do not represent it with the potential, right? It's you just represent it mathematically. Otherwise, it will be infinite spiral that makes you go down. It's something that is not typically visualized. But if you are doing it in momentum, so it's momentum x and y, then kinetic energy is square of momentum, right? It's a parabola. And if in momentum space, if we do not have, if magnetic field is zero, then momentum is conserved. Wave packet will not move anywhere. But if we launch magnetic field, this wave packet will start changing shape in some way. I don't know if it is truly so, or maybe there are some bugs to debug. And this shows kinetic energy, so it's swings between kinetic and magnetic part of energy, and initial wave packet distributes. What is interesting, it doesn't go too far away from initial area, so its total energy is expected to be conserved. And these two animations are connected. So ideally, when it is expected that both position space and momentum space, there will be circular motion of this two-dimensional wave packets. I don't know what is better here. I think it is the same thing. Just in the removing the potential and looking onto distribution and momentum. The to avoid errors on the borders, one needs to take broader range and it's yet to be checked and debugged, but right now the main goal is to set up skeleton that is potentially a good thing for competitive proposal. So these previous figures were dealing with free space, with no atoms, no potentials, only magnetic field and kinetic energy. But the keyword is quantum materials, so it's something real. And here it is something I did this morning with a debug queue for half an hour, so it's not very high precision. So it's 8 by 8 grid points, and it's a little larger than single unit cell. It's like 8 carbons, two-dimensional supercell. And here are energies of frontier orbitals, HOMO and LUMO, as function of momentum in x and y. I don't know why on textbooks and in Wikipedia there should be 6 Dirac points. Here I see only 2. So it's this is not yet competitive figure. Maybe if one the unit cell should be hexagonal and it should have only 2 elements. And this, if one increases size of unit cell, maybe there are some additional effects. And spacing of these grid points is not sufficient. Is like 8 by 8, while for the free space simulation on previous slides it was like 50 by 50. So in order to import, so the idea is to import energies of all these points from electronic calculation and place them here, so that motion of wave packet will experience this dependence of kinetic energy of momentum, which is different from free space, and will already include all features of materials, right? And then include the magnetic field in the same way as we did before. And what will come out is unknown. Or maybe if one looks through multitude of theory and experiment paper, maybe there will be some hints. But before we had wave packet motion around center of parabola. Here I do not have intuition to tell what will be the motion of wave packet. Will it be around this Dirac points? Will it be somewhere else? So it's an open question. And, it could be, I want to hope that it is something competitive to offer to agency. So this is something that can be completed relatively quick and can be applied with minimalistic effort of debugging, and can be applied to a range of two-dimensional materials. Like if one takes the materials that David is exploring, unit cells are a little bigger, and making 50 by 50 key points could take longer time, but in principle it is only a single point calculation. For this part, for electron dynamics that doesn't dissipate energy, for energy conserving dynamics, even with magnetic field, numerical expense is cheap. And it can be applied in a short time to a range of materials. But what, and this can be done probably by anyone in the world pretty soon. So this is time-sensitive thing. But how to, is it possible to combine these features with major strengths of several computational chemistry group at this university to description of the non-radiative relaxation? All these exotic properties are typically explored at liquid helium temperature, because at high temperature all these nice features are suppressed. But at which degree are they suppressed? Can we determine temperature, maximal temperature at which useful effects like this circular currents will still exist. So if one redo these calculations along nuclear trajectory, then it will be super expensive. Instead of one calculation, 50 by 50 K points, it will be like 50 by 50 by 1000. So it's very ambitious. So highly likely energies of at each K point will move. So it will be like breathing dispersion curve. And due to nuclear motion, the states will be not orthogonal to each other. There will be transitions both to other bands and inside one band with dissipated transitions that are not like here. Magnetic field induced transitions do conserve energy. Typically, they go on the tangential line. And if one would include non-radiative relaxation, they would go either to the center or to the nearest minimum, and they will dissipate energy away and stop this circular current. This could be very valuable to assess the strengths of specific material if these non-usual effects will be possible to observe at room temperature, or at least something a little higher than here. And here are results from Fatima. They are one-dimensional, but there is momentum and energy. It changes, the wave packet changes both expectation value of momentum, expectation value of energy, and fluorescence. The goal, if one wants to pursue this research direction, is to generate the same type of data, same type of dynamics, where momentum will be not one-dimensional but two-dimensional. So it will be like surface for occupied orbital, surface for unoccupied orbitals, and wave packet will depend on momentum along x, momentum along y, and energy. So it will be like object that will move in 3 dimensions. And in presence, or like at low temperature, relaxation will be very slow, and wave packets will be able to perform circular motions. At higher temperature, they will relax to a terminal point and sit there no matter how strong magnetic field is. And these features will be different for different materials, and it will be a positive outcome of the research if it is completed. So, free space in position, free space in momentum, the magnetic field induced motion in realistic electronic structure based dispersion curves, and then combining this magnetic field induced circular motion with non-radiative transitions due to non-adiabatic dynamics. And maybe one can also later on, by now it's more than enough, but one can also bring electric field and see a response, like will this circular currents be responsive for electric field perturbation? Could it move continuously across the sample or conductivity? Okay, let's send. I'm done.